So it does go back to calculus 1. You can use this same formula for calculus 1 implicit derivatives. I'm just setting this up because, again, I'm trying to give you an idea of what your homework's going to be like as you go through 14.6. So let's do this. I want to calculate the partial of z with respect to x, but again, notice in this case, the only alternative, it would be to solve for z as a function of x and y. I could do it that way, but look at the hot mess you're asking for if you try to solve this for z as a function of x and y. If that were the only z right there, no problem. But you got this use of z, you got this z cubed, and another linear z, so this would be, I'm going to want to say an impossible mess. You can't solve this for z as a function of x and y. So, if I want to talk about that rate of change,
is that 2 or z?
That's
no.
That's a 2.
That symbol right
These
there.
2's have no loop.
That's the number 2.
Okay.
Yeah, my z's usually I put a little fork through.
Okay.
Because sometimes they look like my 2's if I don't.
And then the
So yeah, I try to put a little.
It's just-
I try to put a little
trying to
slash
figure
in
out-
my z, so my z's have little swords and little arrows stuck through the middle of them. You've been impaled. So, according to my implicit derivative calculation, if I want z's partial with respect to x, I need to do negative fraction of f's partial with x over capital F's partial with z. But keep in mind, I haven't really defined what f is yet. F always comes from your surface. So essentially, it's just the variable expression that's in your surface. Just the x squared z plus z to the third plus zy squared minus 5xy. And in some cases, you have the function equal to a constant or equal to 0. I've usually seen teachers bring that number over and set it equal to 0, because when you do these partials, what's going to happen to that 2 anyway? It's going to go away. So when I do this implicit derivative, don't forget the negative in the front. It's easy to forget that because it just sort of carries one step to the next. If I do this derivative here with respect to x first, just go ahead and put that entirely in the numerator. That's going to be 2xz plus 0 plus 0 minus 5y. So I guess I gave myself way more numerator than I needed. So yeah, that all shouldn't be there. But that's all you need for the first part. And just to play it safe, if you're in the habit of putting your minus a little too high, you might want to do that to sort of protect that numerator from the minus. I usually just put it in the front so it's kind of parallel to the fraction bar, but it technically hasn't affected those signs yet. If you did want to distribute that, it would turn this to negative and turn that to positive. So if you want to make sure, just shield your numerator from the negative sign, so that way I know that you know it hasn't been distributed through yet. Okay. Divided by f's partial with z, which one term at a time, that's going to be x squared plus 3z squared plus y squared, and then everything else goes to 0 because you have no more z's left. So that is your implicit derivative of z measuring rate of change with respect to x. So it's technically a partial derivative on something that's not really a function. Okay. And then, you know, the usual other one you're going to be prompted for is to switch gears. You know, z's rate of change with x, and then compare it to z, or calculate z's rate of change with y. Similar idea. You just use the specific formula you need there. Capital F's partial with y over capital F's partial with z. And second verse, similar to the first. So start with a fresh copy of your f. Its partial with respect to y is going to be 0, 0, 2, for some reason I have alphabetical order going screwy there, but 2yz minus 5x. So there's your complete f partial with y, and then divide it by f's partial with z. Well, you're going to keep the same numerator that you had in the first one. So if you've already done z's partial with x, just copy down the denominator you had from the first one. I think I meant to say denominator. Yes. It's going to be the identical denominator from that first one. Yeah. There you go. Y'all okay? Any questions?
So do we do anything with
I'm
those
picking
from
up on
there?
the raised eyebrows, but I think that's just you saying, I get this. When I see you raise your eyebrow like that. Yes, sir.
So do we do anything with these from here?
No, this is it.
Do we do anything with them in, like, later sections,
well,
or?
no, the really cool thing, to make it turn into something you can actually see, it's just cool to go back Well, to go back to like the implicit derivative section in Calculus 1, which I think that was a chapter 3 topic. And just to kind of remind yourself of some of the hot mess things you had to differentiate there. Like number 38 here.
Nice.
You know, this was most likely a tangent line problem. Well, I can double check the instructions. The instructions down here in the bottom of the previous page. Find the equation of the tangent line at the given point. So you've got this crazy relation here, and I can graph that on the software if you want to see what this funky graph looks like. But it's not a function. I can't solve for y depending on x because that'd be just kind of hard to solve for y. So, but it still produces a graph. And since it has a graph, we can talk about tilt and slope, rise over run, and we have a point on the graph. So if I were doing this the Calc 1 way, this is a product. I'd have to do, you know, f prime g plus fg prime. And remember, every time you do a derivative for y, you have to multiply by that dy over dx term. And then minus, boom, another product rule. Or if you wrote it as x over y, quotient rule, along with the dy over dx rule for every y derivative that you do. Then you have to go through all the algebra of getting the dy over dx stuff on one side, the non-dy over dx stuff on the other, and then divide at the end. So you ultimately always end up with some kind of quotient. But if I do this the Calc 3 way, if I do it the way we did it tonight, I would call this, markers over here, I would call this the capital F. And if I wanted to get the rate of change of y with respect to x, I just need to remember, if y is up top, I need partial with y in the bottom and partial with x in the top. That's it. Do you remember Daryl teaching you something kind of like this? Because it may be a rumor. I could have sworn I'd heard some students say that he teaches the Calc 3 way, which always made me mad because that's such an easy way to do implicit derivatives. And in Calculus 1, you do it the brutal way when you see it as a Calc 1 student.
We went through it.
Everybody had to run through that reading.
back
Everybody had to do it
way.
the tough way. So now if you see it this easy way, you can set this equal to 0 if you want to, so bring that over as a minus 2, okay? And then do this partial with respect to x, which, oops, don't forget your minus sign, Crossland. So there's my minus sign right there, okay? This partial with x, y squared is a constant, e to the x squared minus 16. One extra thing I need to multiply that by would be what?
2x.
2x because of the chain rule, the partial x derivative chain. So technically put a 2x in the front there. And then, so that's done. The partial here with respect to x is linear, so that will be minus y to the negative 1. Okay? So the numerator of your derivative is done. You now need to switch gears and do the partial of this with respect to y. So then this partial with y would be 2y, and leave the e expression alone. And then this derivative with respect to y, be careful that negative and negative would be positive xy to the negative 2. And the only edit I can imagine the back of the book doing is most likely you want to get rid of those negative exponents. So if that was done, you could remedy that easiest by multiplying the top and the bottom of this by y squared. You see why y squared is going to be the handy thing to use there? Because it gets rid of both negative exponents. And again, that's just one of those algebraic clever forms of 1 that you've used in the past. So it's not going to change the value, but it'll change the way it looks. So if I did do that, that would make my dy over dx look like negative, still in the front. Sweep that across here, that's going to become 2xy to the 4th e to the x squared minus 16 minus y, distributing that y to the 2 up top. Distributing y squared to the bottom, you get a 2y to the 3rd, then your exponential, and then plus x, and there you go, plus x.
If I could swallow my original statement and modify it, I've seen it before.
You have seen that
yeah.
before. Okay, so you do. So he does do some kind of version of it. He probably. So you actually saw partial derivatives in Calculus 1.
Yes, sir.
Yeah. So I'm not mad. I'm not going to go kick down Daryl's door or anything like that. Apparently he's been doing it for several semesters. But And, oh God, you're gonna post this on YouTube. Anyway, I'm not trying to slam Daryl, don't get me wrong, you know, he's a great guy, he's a wonderful colleague. But I wanna double check and see if this is right. Oh, heck, it's even. So, yes, it's right. It is correct, I promise. Feel free to go back to Calc 1 and check it the Calc 1 way, but that makes the Calc 1 implicit derivatives a heck of a lot easier. Okay. So, do you feel fed tonight? You're almost, it's almost 8:05. If you hang out until 8:05, you'll get to hear my end of class alarm. I set an alarm to let me know when class is over so that way I don't go over. So we're technically done, so you can go and start shuffling your papers and getting ready to head out. Any last minute questions about the test or?
So
You'll probably
have an
think of
option
some
to
between
retake
now
it?
and, pardon?
So we have an option to retake it?
Yeah, I'll do that for test 2 and for test 3. It's gonna be, I'm gonna say nigh impossible to do it for test 4 because that's final exams week. But you have the option of retaking test 2 and test 3. And I guess, I mean, is anybody, you mentioned you're interested in taking test 1 over. The Imperial March, that's your end of class
I'd like
one.
to take it.
You mentioned taking test 1 over, so if Beth sends me a copy of her test 1, what I do is just take the problems and do some, keep the same format, and then, you know, change this to this, change this to this, but it'd be the same kind of thing, so that way you can take it and
I'd like to
replace your test
definitely
1
try
grade.
and
You can only do
take
it
another
though,
stab
you can
at it.
only do it for 1 test. Because the final exam would only get to replace 1 test grade, so you only get to redo 1 test.
Okay.
And here's what I'm also gonna require. If you wanna retake test 2, you have to take it before we take test 3.
Okay.
If you wanna retake test 3, you have to do it before you take test 4.
If you want to retake test 1.
If you wanna take test 1, since, is anybody interested, you 2 are interested in taking test 1 over?
Yes, sir.
So a good many of you are, at least 3 or 4 of you, okay. So, test 1 folks, going to get test 2 out of the way, and then we'll cross that bridge when we get to it,
Thank you.
okay? And just kick
whichever
butt on
one's
test
worse.
2. Pardon?
Whichever one's worse.
Yeah, I guess so. Replace the worst one. So you have yet to even have a plurality of grades in this class.
Yeah.
So let's see how test 2 goes,
Make it rough.
and whichever one the worst one is, the one that we want to retake. But hopefully you'll do well. You won't need to.
Yeah.
Any other questions?